So I was giving this example. Suppose D is a metric on X. Now you take new metric D1. D1 of XY is equal to twice DXY. You can easily check that this is also a metric, and that 2 is not very important. Take 3 or 4 or 5 or root or anything. So you can get plenty of metrics, but understand one thing. In this D1, which is D1 XY is equal to 2 DXY. If you take any ball of radius R in D1, it is the same as a ball of radius half R in the other one. In other words, every open ball in D1 is an open ball in D, and every open ball in D is an open ball in D1. So D and D1 are different metrics, looks like, but we say that as far as open balls are concerned, they both produce the same collection of open balls. Therefore, as far as metric is concerned, produce the same. Then it will be a limit point of A in D1, and if C is a limit point of A in D1, it will be a limit point of A in D. So open balls are a little more general than specific metrics. That's the first thing that I wanted to say. So there is a little extra improvement in looking at from this point of view, that simply look at the open balls, forget about the metric. Of course, it's not a very great improvement. Let's go ahead, one by one. So that is the first advantage that we had. Now, the next thing that you should understand is, this is the point we make a small, twist. So if every open ball intersect A, then anything bigger than that also will intersect A. So, and think of it what I'm saying. C is a limit point of A if every open ball around C intersect A. So if an open ball intersect A, if you take a subset bigger than an open ball, that should also intersect A. It's a very simple observation. It's not a big thing. In fact, mathematics often goes with such very simple observations, which completely, changes the mode of what we do. So, so look at that way. That means C is a limit point of A, then every open ball around C will intersect A. And therefore, every subset bigger than an open ball. That means if you take any subset U that contains an open ball around C, that will also intersect A. Because once BC epsilon intersection A is non-empty, any subset bigger than BC epsilon C is a limit point of A. Every subset, there are two sides. Let us look at one side. C is a limit point of A. Then every subset of X containing an open ball around C will intersect A. That's one side of it. Why is this true? So look at U that contains an open ball, say BC epsilon. So BC epsilon is contained in U. So, but BC epsilon will contain an element of A because it will intersect A. So that will belong to U also. So therefore, U will contain an element of A. So this is true for every subset containing an open ball around U. Probably I have a picture. Yes, here is a picture. So what we are saying is, take any subset that contains an open ball around C. Since C is a limit point, that open ball will intersect A. Or in other words, there is an element of A in that open ball. So that will certainly an element of U because that open ball is contained in U. So you can see I have plotted it clearly here. So therefore, every subset that contains an open ball will also intersect A. Now we are talking about not just open ball, subsets that are bigger than open balls. There are a lot of subsets on one side, but other side, we are not very, very specific about open ball. So the dependency on metric, though it is there, slightly we are reducing that. So this one step, such sets. What about the converse? If every subset that contains an open ball around C will intersect A, will every open ball intersect A? Because to say C is a limit point of A, we have to ensure that every open ball intersects. But we are claiming that every subset that contains, so let me go back here, the other side. So C is a limit point, then this happens. And the converse is, if every subset U containing an open ball around C will intersect A. That is the assumption. Can you say C is a limit point? What are you supposed to prove? Every open ball should intersect A. So let us take an open ball. But what is given? If it contains an open ball, then it will intersect A. But what have we taken? We have taken an open ball. So obviously it contains that open ball. So it will intersect A. I'll pause a second. If anybody has a difficulty, please let me know. Please tell me. Raise your hand. Please don't hesitate to ask questions, because I can't see your face, neither you can see my face. So, the communication becomes much less effective, unlike in a classroom. So if you talk, then that will make it more lively. So please don't hesitate. So I hope you have understood. Again, go through this proof once again quickly. So first, assume C is a limit point of A. Then what are we supposed to prove? The second part of it. Start with, what does it say? For every subset U satisfying some condition, something should be true. What is that? So start with any subset. What is the condition? Subset containing an open ball around C. You have to show it will intersect A. So start with a subset U that contains an open ball around C. Now you have to prove that it will intersect A. Because our assumption that C is a limit point of A, the open ball that BC epsilon will intersect A. That means there is an element of A in that open ball. And that will be an element of U. Therefore, U intersection A contains small a, so it's non-empty. So one side is done. What is the converse? Assume that every subset U of X containing an open ball around C will intersect A. So second part we assume, and we have to prove that C is a limit point. So C is a limit point by our definition. It's equivalent to saying we have to prove that every open ball around C will intersect A. So let us start with an open ball. Now ask what is given. If you take a subset containing an open ball, it will intersect A. But what have you taken? You have taken an open ball. So that contains an open ball itself. Therefore, it will intersect A. Hence, we prove that C is a limit point. So it's equivalent. So now we are in a new, platform collection. We are no more interested just the open balls, but something more than that. This is the collection. So we are looking at all subsets that contain an open ball around C. So this is the collection. See, let me sometimes, the language can be confusing. So, but you should take the language that I use, blindly, because different books use different languages. The concepts have to be clear. The terminologies could vary. That's what I meant. these elements of C are called neighborhoods. In modern language, these are not. And that is why I'm telling these words, don't take it blindly. Like the limit points that I said, it is not the modern language. It's slightly more, more restricted, but I kept a very general definition. So similarly here, but I don't keep using it except, orally speaking, I just say. So this says, so what we observed is that C is a limit point of A if and only if every subset containing an ball around C will intersect A. That means if you take any element in this script and C, it will intersect A. So this is what it is. C is a limit point of A if and only if for every U in NC, U intersection A is non-empty. So this also you should learn the way to write. Way to write is write mathematics is very, very important. I mean, the language of mathematics. So in this process, you should also learn how to present things very rigorously and, in our own language. So it's very easy once you write this. If I have to prove that, what am I supposed to do? For every U in NC, something has to be proved. So what do? I take an element of NC and then prove whatever is claimed. U intersection A is empty. So reading this, you will understand how you prove it or what does it mean, how do I use it, etc. So make it a habit to use this mathematical language to write things properly. So I pause for a second, for a minute for people to just go through it and see if you have any difficulty. If so, please let me know. Okay. Anybody? I can only keep telling. So yeah, Vishnu has. Oh, okay. Okay. I just want to know if anybody wants to ask a question. Please raise your hand so that we can communicate. Or you can unmute your mic and speak if you like.
Sir,
if nobody speaks, I assume that all of you have understood. Yeah.
Sir.
Somebody. Albin?
Sir, I feel there is ambiguity in the definition and the limit point that you have said. By your definition,
Tell me again.
I think there is a problem with the definition of the limit point, as you have said.
Where is the problem? Yeah, let me know. Tell me.
Okay.
Which one is the problem? Please tell.
C is said to be, you have said that C is said to be a limit point of A set A if every open ball around C is A. But it is not every open ball around
will intersect A.
Must intersect A at points other than C. In that, I think.
I did not give that definition.
Oh, I think
my definition is saying that every open ball should intersect A. That's enough.
Why?
Then that's my definition. See, that's what I said yesterday. I don't know whether you were there or probably you might have missed it.
Yeah, I have missed
it. The conventional definition books will always say other than.
Okay.
And I am not giving that definition. Okay. My definition is that every open ball should intersect. For instance, if A itself is C itself is in A, it's always a limit point. It's irrelevant what it is. Did you understand that?
Okay, and I understand that. Sorry,
so
sir.
Therefore, other. And that's all okay. I understand. That's why I want you to ask these questions. I know that this is always a confusing thing because almost all the books use that. But then there is no no parallel notion or parallel word that is used for this concept.
Okay.
That
Oh,
every open ball will intersect.
okay. Thank you, sir.
See, I use yeah, that's fine. When yesterday I said this, this confusion is always there, not only with you. Many people have it. Others might not have asked. You asked. That's fine. I want this discussion, and that's what because I can once again explain. See, if every open ball intersect at a point other than C, then I call it a cluster point. Physically, there are a lot of points clustered. But for limit point, I would like to just, very general. As long as every open ball intersect A, contains an element of A, enough. Okay? That language helps me to, work out very conveniently. Without which it will be very tough. So that is why I use this language. Is that okay? I mean, this is for all of you. I mean, yesterday also.
Yeah, okay, sir.
Okay, good.
Okay,
So
sir.
now let's go ahead.
Okay.
Yeah, fine. That's fine. So let me come back. Yeah, C is a limit point of this if and only if every neighborhood. So this is the classical. This is a classical definition of neighborhoods, not the modern definition again. So every neighborhood of C intersect A. But what it means is a neighborhood is a subset containing an open ball around C. So now we have we are slowly getting out of the clutches of this metric. Metric in disguise was present in open balls. Now even we are making much general where the metric dependency is slowly getting reduced. But does it do some good purpose? We will see. Okay. So, but anyway, I could introduce this new thing called neighborhood system. So this NC, you could call it neighborhood system. So if you give me neighborhoods, that is enough to decide limit points. No metric is required, not even open balls. I don't even ask that question. Whether these are, what are the open balls? As long as you say that this is the collection of all subset that contains an open ball around C, then that is enough. So no metric, no open ball, only this collection. So we have slightly, slowly coming out of the. Now, in the study of limits or in the study in generally mathematics, we define some structure. And then we look at maps that, preserve structure. I'll give some examples. For instance, what is a structure? It's a very vague term. You take some objects and using them do something and produce a new object is probably the structure definition. For instance, very simple definition is, example is addition. Addition is a structure on, R. What does it do? You take two elements and then give it sum or ordered pair, all those rigorous definitions, don't worry about it. Similarly, multiplication of real numbers or wherever it is defined. In group, you talk about binary operation, which is a structure. Given an ordered pair of, a pair of two elements, which is properly ordered, it will produce a new element called its product or sum or whatever terminology. Similarly, in analysis, the structure that we are interested in is associating limit points. For subsets, you associate limit points. That's the structure in analysis. So now we want to ask the question, relation between, spaces, in analysis, namely structure preserving maps. For instance, if you look at our simplest example is, say, let us look at in R. Let me go to the yes. This is the slide that I want. F preserves addition. What does it mean? It means that suppose you take sum of two real numbers. First, F is a map from R to R. I have not written here. F preserves addition is what I'm telling you. What does it mean? F preserves the structure. The structure here is just addition. So take two real numbers A and B and look at its sum. Now you look at the image. What is the image of FC? C is the sum of A plus C. Then FC must be the sum of images. What are the images? FA and FB. So your FC must be, the image of C must be sum of the images. So this is what it is. That means image of the sum is the same as the sum of the images. So you can see that this is exactly what. So first you take the image and then sum. That's what you have done on the right side. On the left side you have done, first you took the sum and then took the image under F. You will end up getting same thing. Either you take sum and then take the image, or you take the image and then take the sum. You are going to get the same. So this is what is meant by saying that F preserves addition. In most of you, you write, instead of C, you write here A plus B itself. So this is the way you write it. Basically, that's what it means. So you first add A plus B and then take the image under F, or you first take the image under F, so FA and FB, and then add. So both should get same thing. The map and the binary operations in some sense can be taken in either order. That is what it is. First addition, then image, or first image, then addition. You get. This is what is called addition preserving. Similarly, multiplication, you will be immediate. The last line will tell you what is meant by structure preserving. So multiplication preserving map means A into B is equal to FA into FB. Similarly, in linear algebra, these are the general structure like group theory. You must have done this. G1 to G2 groups, G1 and G2 groups. F from G1 to G2 is a group preserving map, group operating structure preserving map. If F star B is equal to FA star FB. So this same pattern, exactly same. Any algebraic structure, that's all. In linear algebra, what is a structure preserving map? Of course, in group theory, we call it homomorphism. In linear algebra, what is that? F of sum of two vectors is sum of the images, F of them. So F of U plus V is equal to FU plus FV. Similarly, image of the scalar multiple is scalar multiple of the image. F of alpha V is equal to alpha times FV, and so on. So this is the algebraic thing. Now, let's come down to our structure. Can anybody now tell me what is expected to be structure preserving map in analysis? Analysis, the structure is associating limit points to subsets. That's the structure in analysis. So now, if you understood structure preserving maps, the general concept, can anybody tell me when do you say that a map preserves the structure? Think about it. If you don't get an answer, don't worry, because you might not have looked at it earlier, but this is the time you should think these things. Okay? Yeah. If anybody has an answer, please raise your hand. It's very, or, yeah. Yes, I don't get any answer. Some of it, we should learn thinking. This is very important. Mathematics is, a mental game. So we should always try to think so that, you will get some ideas.
Sir?
Who's this? Shiva?
Yes, sir.
Tell me.
If C is a limit point of A, then f of C is a limit point of f of A.
I didn't hear the first part of it.
If C is a limit point of A, then f of C is a limit point of f of A.
Yeah, okay. So I hope you others must have heard what she said. So you take limit point on the left side. So you have a subset and a limit point. So C is a limit point of A. When do you say F preserves that structure? It's very natural. You take the image, then the image has to be the limit point of the image. Image of the sum has to be the sum. Similarly, image of the limit point has to be a limit point. It's that simple. Image has to be the limit point. The image of the limit point has to be the limit of image. So first take the limit and then take the image, or first take the image and then take the limit. You are not going to get something different. I mean, that's not exactly correct. So I'm just, it is slightly more than what in the algebraic structure, but don't worry about that part. I'm not even getting into. So that's what Schiffer was telling. If C is a limit point of A, then you look at the image FC, it has to be a limit point of FA. So let us, I hope I have written it. Okay, so this is fine. Yeah, what is the meaning of saying F from X to Y preserves limits? So F should map limit points to limit points. These are vague terms. So now the question is, for which maps does this? That we don't know. Because only such maps are considered as good maps. Good in groups, you will have a lot of maps from group to group, but none of them we take as good maps. Good maps are the ones that preserves the structure. They are called homomorphisms, and so on. Linear maps in the case of vector spaces, they are structure preserving maps. They are called linear maps. I mean, different words are used. So in this case, we have to find out what condition on F will ensure that it is a good map. In other words, it preserves limit points. So let us, now we are going to invent that. We have not made any condition on F. So let us look at map. So we have to somehow find out what condition we should put so that it will preserve limit point. So let us start with the limit point, the subset A of X, and okay, I think this is just the write-up. This is what our aim. We consider maps that preserves limit. So this is what we want. If C is a limit point of A, then FC must be a limit point of FA. Of course, one is happening in X, the other one FA and FC are in Y. So the limit point is taken there. So we will say what condition on F will ensure us. That's what we are going to invent. We have not made any condition. We are going to explore and see what we should do. Okay, so maybe, yes, let us start with all this. Let's look at the picture. So we have, X and Y metric spaces, and F from X to Y, we have a map. So let us plot A, okay, take a subset A and limit point. So let me just plot it. For some strange reason, I put it on the boundary side, but that's not very important. It's just to give a feeling that, it is very close and maybe in A, may not be in A, all that. It doesn't matter. Now look at its image. That is the idea. So what is the meaning of image? Look at all the points of A, who's the image of A. So which is, now we ask this question that we are looking for. Under what condition FC will be a limit point of the image of A? Image of this notation, I suppose all of you know, must have seen. Look at all the, the images of all the elements of A. So that will be a subset of Y. F capital A is nothing but images of set of all images of elements of capital A. Okay, so that notation is given here, definition with the definition. So let us see this. So I have just plotted this. Now our aim is to find some condition under which FC will be a limit point of this. So let us plot FC for some. This plotting is, I tell you, it's just to give a feeling. They are not true pictures or anything. This is always good to, practice. That you plot some diagram and then look at them, then it will be easy for you to understand the concept. But ultimately, you will have to rigorously prove whatever you want. Okay, so that these are not proofs. These are the ones that gives motivation to intuition, understanding to the concept. So now our aim is to show that, to find some conditions such that FC is a limit point of A. So let us see, when will FC is a limit point of A? Let's look at our first definition. Every open ball around FC should intersect FA. Then we are done. That is what, so what condition ensures that? We don't know. But remember, what is given, you should never forget that F is a map, A is a subset of X, and C is a limit point. This is the only thing given. We have not put any condition on F. So we are going to look at what condition we should put. So let us start, explore when will FC be a limit point of A. So start with an open ball around FC. Okay, so let us start with epsilon positive. That's the radius of the open ball, I mean. Well, I have not written, there is not enough space to plot that. So what that red bounded color boundary region is the epsilon ball. So we have to show that every open ball around FC will intersect FA. So let us start with an arbitrary open ball around FC. So the radius epsilon is an arbitrary positive real number. Now, what is that we are looking for? We have to show that it will intersect F capital A. What does it mean? There must be an element of F capital A in this open ball, that red colored region. How does that ensure? What does that mean? That means what is meant by F capital A? You must produce an element of capital A whose image is inside this. So that when can this happen? So, but we don't know whether this will happen. I mean, how will we find out? So what we look at, let us look at all the points that are mapped inside this open ball. So what is that? Where are they? They are all elements of X whose image is contained in this open ball. Remember, C will always be there because FC is inside the open ball. FC is the radius, is the center of that. So certainly it is inside. So let us look at this collection. Well, this write-up, be careful while reading because it is, this is the set of all elements of X whose image is contained in that red colored, open ball. So it is certainly a subset of X. There is a notation I have given here. May be useful if you like, it doesn't matter. This is the inverse image of the open ball. That this red open ball that you see here in this picture, yes, it's inverse image. So sometimes it's called inverse image because it is, you are coming back to X and take all the points of X whose image is inside that. Okay, so I mean, I can give a diagrammatic, representation. Yeah, now you see that. So that on the left side, again, I marked the set of all points using red boundary, and that arrow says this whole set is mapped inside this epsilon ball. Okay, so that now, okay, so we have understood all the points of X, or we have taken all the points of X that are mapped inside this open ball. But the question is, will that contain an element A? Then its image will be inside this open ball. Will this left side set F inverse of that open ball, will it contain an element of A? So that's the question. So let us ask what is given now. It's given that C is a limit point of A. That means every open ball will around C will intersect A. But remember, I mean, it is too hard to expect that this would be an open ball. That will be too restricted. But we have already also seen another, that C is a limit point if every neighborhood of C intersect A. That means if this region, red colored region on the left side, if it is a neighborhood of A, then certainly it will intersect A, because C is a limit point of A. What is meant by neighborhood? If it contains an open ball inside that. So that is the minimum requirement, without which you will not be able to get. So what we do, we claim, now we impose this condition that this region on the left side, colored left, will contain an open ball around C. That means it's a neighborhood. So now I have written F inverse of this open ball. That is the one that we have plotted with the red boundary on the in X. That should, if that contains an open ball, then we are done, because every open ball around C will intersect, or it's written as around X. It is not X, it's around C. Every open ball around C will certainly intersect A, because C is a limit point. So now that's what we are going to demand. This set, that red colored region on the left side, will contain an open ball around C. That means inverse image of this epsilon ball will contain an open ball around C. That means there is some positive real number. So let me see the picture first again. Yeah, look at the picture. So what we demand is, so far we have not put any condition on F. Now we are putting a condition that if you take an open ball around FC, and look at its inverse image, it should contain an open ball around C. That's the condition. If you demand, then we are done, because C is a limit point of A. Therefore, this black colored open ball will certainly intersect A. And every element of this red region on the left side will be mapped to the open ball on the right side. So in particular, elements of C, this black colored open ball, also will be mapped inside the epsilon ball. So in particular, there are elements of A that are such that open ball of radius delta around C is contained in the inverse image of the open ball of radius epsilon around FC. So in inverse image of every open ball will contain an open ball. A very, very crude way of saying. Of course, it contains an open ball means it's a neighborhood. So F inverse B FC epsilon has to be a neighborhood. This should happen for every epsilon. Then F will preserve limit point. In other words, if C is a limit point of A, FC has to be a limit point of F. So that is the definition. So I do not know whether you have realized what is the definition that we have arrived at. This is exactly what you must have seen in your earlier courses called continuity. So given epsilon positive, you started with an epsilon positive. We say there is a delta positive such that whenever the distance between X and C is less than delta, F of okay, I mean this its image will be inside the open ball of radius epsilon, or in other words, distance between fx and fc will be less than epsilon. This is what continuity is all about. So the definition of continuity is actually imposed to ensure that f preserves limit points. Okay, so let's just check this, complete the argument. And somebody is asking some question. Hello? Anybody asked some question? If not, I will continue. So now we demand this. There is a delta positive such that this delta ball is contained in that. So maybe now remember, so we complete our argument. A is, since C is a limit point of A, there will be an element A intersection C delta will be non-empty, or there is an element of A belonging to that. So of course, BC epsilon, BC delta is contained in F inverse B FC epsilon. That's the condition we impose. Therefore, A belongs to A intersection this. So let's look at this picture. So now, of course, I have not plotted I have not written the name. Then you can see that dot I have put. There is an element of A belonging to that delta ball. Delta ball is that black colored ball, but which is contained in the red region. The red region on the left side is set of all points whose image is inside the epsilon ball that we started on the right side. So in particular, this delta ball also goes inside, and even that element of A which is inside will go to, so that's an A. So its FA will be mapped to the epsilon ball. So FA belongs to FA, which is intersection BFC epsilon, and hence C is FC is a limit point of FA. This is just a completion of the proof. So you can see that this A belongs to that dot that we obtained, that because C is a limit point of A, we get an element of A in that delta ball. But this whole set is mapped inside this whole set is, where is it? Yeah, this whole set is mapped inside this epsilon ball. So in particular, this dot, this A is also mapped inside, so that FA belongs to this epsilon ball. So this epsilon ball intersect F capital A. So FC is a limit point. So this is what we are going to demand. So for every epsilon positive, there is a delta positive such that the delta ball around C is contained in the inverse image of this, or equivalently, these two are equivalent. BC delta is contained in F inverse of this. By definition, this is a set of all points whose image is that inside the epsilon ball. So BC delta is contained in that. That means every element of BC delta is mapped inside the epsilon ball. So F, the image of BC delta is contained in B FC epsilon. I mean the epsilon ball there, which I'll go to. This is the picture. I have not drawn that black colored object on the right side, which will appear inside this epsilon ball. That image of the delta ball, which is colored in black. But of course, it will not be a ball. It will be some subset, but it is fully contained. Quickly say continuous. That's the word we used. Now we don't know structure preserving, etc. So we arrived at the condition that is necessary to ensure that limit points are mapped to limit points. And the condition is that given any epsilon ball around FC, there must be a delta ball around C whose image is contained in that. That's it. Or the delta ball is contained in the inverse image. So that's called the word used is continuous. So f from x to y, c is in x some point, then we say that f is continuous at c if for every, this is the standard definition. So I don't really have to, I have not written, expanded this the conventional way. So you can equivalently, you can say there is a delta positive such that f of the delta ball, image of the delta ball is contained in the epsilon ball. So if you look at this way, it is easy, because if you take any element in x in the delta ball, that means distance between x and that means fx, because this whole delta ball is inside. So fx is inside this epsilon ball. That means distance between fx and fc will be less than epsilon. So this is a modern definition of continuity. And this is what is required for limit point preserving maps. Okay? So with this, I stop for a while, and I want you to think of it. If there any doubt is there, please let me know. If anybody has anything to ask or comment. Any doubt? I don't. I don't know. Is monologue talk? I don't like it. I want people to participate. Yes. Nobody wants to say, make any comment or adding whatever I said. Even that's fine. If anybody has a suggestion or anything, I like it. Okay. So if nothing is there, then I will have to move ahead. Okay. Now, of course, let us improve into what we have said. So what we said is that inverse image of every open ball contains an open ball. This first part of the definition says contains an open ball means what? It's a neighborhood. Let us go back to our original, our new terminology. This says that inverse image of every open ball should be a neighborhood. So inverse image of every open ball around FC will become a neighborhood of C. If that happens, then F is continuous. You can see slowly we are getting out of this metric business. That is what I'm trying. So on the left side now we ordered of the language of metric spaces. Wait. Yeah. So for any subset A, C is a limit point, then F is continuous at C. This I want to just give some exercises for you. Yes. Suppose we assume F is continuous. Now we have this, we arrived at this definition thinking that this would do our job. That if we define this, F will preserve limit point. Now we have to confirm this. That is a good exercise for you. Assume F is continuous. So the definition is here. Now forget whatever that we have done. Here is a definition. Like in any class, normally what most people do, brutally write this definition. So there is a first definition, limit point. Second definition, continuity. And here is an exercise. So go exactly like what probably many teachers do. Actually, we arrived at this. We pretend as though we have not arrived at or anything. Now we have this definition, whether this will do the job. So F continuous at C. The definition is here. I've already given this the standard definition. Then, now here is a conclusion. If you take any subset A with C as a limit point, FC is a limit point of FA. In fact, this is how we started. Look at FC as a limit. Suppose it is a limit point. What are the things that is required? And then we came back and said, if we put this condition, then that will ensure that it is going to be a limit point. So that is what we arrived at. So this is an exercise now you have to do. So you only have that definition that given any epsilon ball, there is a delta ball whose image is contained in that. Now show that FC is a limit point of FA. So that I will leave it to you. Tomorrow morning, and tomorrow's lecture, if anybody is in difficulty when I come, when we return, please, you can ask me. We'll again listen in case necessary. And then now it is not enough. I will give you one more. Get back to the other way. What is that? If F is continuous, then F preserves limit point. Now we assume F preserves limit point. And for any subset A of C, A with C as a limit point, FC is a limit point. We assume that. And show that F is continuous. This exercise is probably a little more involved. So try. I want you to look at this and see how will you do. It's very interesting. So try to see. And then if both these are done, that means F is limit point preserving map if and only if F is continuous. That's the conclusion. The two exercises together, limit point preserving is equivalent to continuity. So that is the reason. I mean, the structure in analysis is actually, taking limit points. And where maps that preserve limit points are the structure preserving maps. They are precisely the continuous functions. That is what we have seen. So this is the final statement. F is continuous at C if and only if. Okay, I mean, I've written more precisely. Now let us look at this. Oh yeah, I want to get out of this again. Okay, so we said that inverse image of every open ball should contain an open ball. That means it is a neighborhood. So as I was mentioning, left hand side we have got out of this open ball language. We got to do neighborhood language. Every open ball is going to be a neighborhood. What more we say? Can anybody say more than this? So inverse image of every open ball is a neighborhood, because the inverse image of every open ball contains an open ball. So any subset containing an open ball is called a neighborhood. So we use the new language. A picture also you remember. And we also demanded. That is our condition. So inverse image of open balls are neighborhoods. So what is that you want to say a little more than that? I want to come out of this open ball business. That's the idea. Anybody? I want some suggestion. People have to come out, and then only it becomes interesting, right? And we have enough time. That is, otherwise I would have just, monologue. I would have finished. And that doesn't look nice. You should learn things then. To learn things, you always have to discuss. So, well, see, on the left side, we only have to know, left side, I mean, in X, we only have to know neighborhoods. But the right side that we are talking, we are taking open balls. Can I get out of that? That is a question. More precise question. Inverse image of open balls are neighborhoods. So left hand side, we need to know only neighborhoods. And right hand side, do we have to know open balls? Anybody? Any suggestion? What will happen if you take a neighborhood on the right side? Neighborhood of FC. Right side, I mean in Y. If you take a neighborhood of FC, what does that mean? Suppose V is a neighborhood of FC. What does that mean?
There is an open ball
around FC.
containing f of c.
Who is speaking? Let me see. Oh, this is atrocious. Wait a minute, I made some error in this. Okay, I think I'll go back again. So I don't know. I mean, I missed that. Okay. Yeah, who said that? Anuja?
Sir, I spoke the same
Hello?
that you said.
Okay, fine. So if you take a neighborhood of FC, it will contain an open ball around FC. So I think I lost this presentation now. Yeah, it's okay. Can you see the presentation now? Yeah,
Yes,
that's
sir.
fine. Oh, I'm sorry. I'll go back to the slide. Is slightly missed. No, I don't see. Sorry for the confusion. Over. Yeah. Yeah, this we have concluded. Let me stop somewhere. Exercise. Okay. So if you take a neighborhood of FC, it will contain an open ball. So U is a neighborhood. That means there is some open ball BFC epsilon contained in U. But what do you know about inverse image of open ball? It will be a neighborhood. It will contain an open ball around C. So what about inverse image of U? U contains an open ball. Therefore, inverse image of U will contain inverse image of the open ball, which contains an open ball around C. That means inverse image of U will be also a neighborhood of C. So probably, well, I was a little quick in telling this. Yeah, let me give this picture. It's not a complete picture, but let's look at this. So you take a neighborhood around FC. V is a neighborhood around FC. What does it mean? V contains an open ball around that. So now right side also we are only taking neighborhoods, no more open ball. We are going to ignore this language of open ball. So take any neighborhood V of FC, the point FC. Then it will contain an open ball. So now, okay, let us call the radius of the open ball as epsilon. Then what does it mean? You look at the inverse image of that open ball. That's an epsilon open ball. It's a subset of X. But then you know that it should contain a delta ball because F is continuous. So it will contain a delta ball. So inverse image of V, which I have not plotted, will be actually bigger than this red region. Because V is bigger than this open ball, so its inverse image will be bigger than the inverse image of the open ball. Unfortunately, I forgot to draw that. The inverse image of V will be some subset U, which is bigger than this red bordered region in X, and that contains a delta ball. So that's going to be a neighborhood. So what we have proved is that inverse image of every neighborhood has to be a neighborhood. Every neighborhood of FC has to be a neighborhood of C. So now you can see the way slowly we are coming out of the language of metric spaces. Avoiding the metric notation, then we came to open ball. Now we have more general terms called neighborhood, where open balls are also not the actual candidates. It's more than that. It's the same thing is written. F is continuous at C. Then for any subset V containing an open ball around FC, that's what the picture shows. There is a subset U containing an open ball around C such that FU is contained in V. So that's the same thing. For any around FC, there is the same thing written. Yes. The converse also we have to now see. Suppose we assume this. That is what. Okay. I'm sorry. So we assume F is continuous at C. Then we prove that inverse image of every neighborhood is a neighborhood. Now ask this converse. Suppose we assume that for any subset V containing an open ball around FC, that means any neighborhood of FC, there is a subset U containing an open ball around C. That means there is a neighborhood U of C such that FU is contained in V. This is the assumption, and we have to prove that F is continuous. So assumption is that inverse image of every neighborhood is a neighborhood, or given any neighborhood of FC, there is a neighborhood of C whose image is contained in V. We have to show F is continuous. How do we show F is continuous? Given any epsilon bond, inverse image should contain a delta bond. So let us start proving that. So let us take an epsilon bond. What we know is that if you give me a neighborhood of FC, its inverse image contains a, there is a delta, there is a neighborhood of C whose image is in that. And what is given is an epsilon bond. Epsilon bond is already a neighborhood because it already contains the same bond. So it is bigger than actually it is equal to an open bond. Therefore it is a neighborhood. So let us call this as V. For this V, you look at the inverse image. For this V, we use the given condition. What is the condition given? Given any neighborhood of FC, there is a neighborhood of U whose image is contained in that. So this blue colored, region, which is a neighborhood of C whose image is contained in that. That means what is the meaning of neighborhood of C? It contains a delta bond. And where will the image of the delta bond? It will be contained in the image of the blue region. That means, what did we do? We started with an epsilon ball and we produced a delta ball on the left side whose image is contained in the epsilon ball. And that is what is required for continuity. Let me go back to this proof again because I was a little quick about it. So before that, let's see the assumption. Assumption is that whenever you take a subset containing an open ball around FC, there is a subset of X containing an open ball around C whose image is contained in V. This is the assumption. And we have to prove that F is continuous. So To show continuous, you remember the definition. Given an epsilon ball, there is a delta ball around C whose image is contained in that. So let's start with an epsilon ball. Now, you are supposed to produce a delta ball. How will you do that? Look at what is given. If you are given a neighborhood of FC, then something happens. So do we have a neighborhood of FC? If you want to use that, you need a neighborhood. What is a neighborhood of FC? A subset containing an open ball. But this open ball itself satisfies that condition. It contains an open ball, that open ball itself. So let us take this as the neighborhood. So V is a neighborhood. Once you have a neighborhood of FC, there is a neighborhood of C whose image is contained in the V. So here is it. So that's the picture. There is a neighborhood of C whose image is contained in V. V is nothing but this open ball. What is the meaning of neighborhood of U? Neighborhood of C? Use a neighborhood of C means there is a open ball around C. So call this. Let us take the radius to be delta. So this delta ball is contained in U, but this U is mapped inside the open, inside V. Therefore, the subset delta ball also is mapped inside the open. So what have we done? We started with the epsilon ball or epsilon. Then we produced a delta such that the image of the delta ball is contained in the epsilon ball around FC, and hence F is continuous. So continuity also can be completely described using neighborhood systems. We don't need metric. We can come out of metric. So somewhere, yeah, same thing. Yes. Now let me write down this. This is the this definition we have already seen, the neighborhood system. And this we have already seen. C is a limit point of A if and only if for every U in U. This is not important because we have already seen this. Continuity, let us write. Yes. F is continuous at C if and only if for every neighborhood of FC, there is a neighborhood of C whose image is contained in that. So now you can read this. Now I have completely rewritten using our new language. So sometimes this is, this way of writing can be a little confusing because we are contracting notations together, etc. So you should learn this art. Okay. So what is given for every V in NFC? NFC is the neighborhood system at FC. So for every neighborhood of FC, which when we write in mathematically, this is the symbol, and way we what is that we are saying? There is a U in NC, that there is a neighborhood of C such that its image is contained in V. So for every neighborhood of FC, you can get a neighborhood. There is a neighborhood of C whose image is contained in that. Or equivalently saying U is contained in the inverse image. These two are equivalent. Fu is contained in V is equivalent to saying U is contained in F inverse V. That is the way F inverse V is defined. By the way, I also want to warn you, there is nothing called F inverse as a map. This is a notation for a set. What is the set? All points whose image is in V. It is not inverse function. This is a very confusing notation, but it's commonly used. It is just one notation. Don't break F inverse and V. F inverse V is just one notation. So that it means all points in X whose image is in V. It's just that. Okay. So, what is the moral of the story? If you want to discuss structure, you only need to know neighborhood system. No metric, no open ball, nothing. Tell me NC, the neighborhood system. Also, if you want to talk about structure preserving maps, again, we don't need don't give me metric, don't give me open ball, just give me the neighborhood system at both C and FC. Then we can determine whether F preserves limit point. That means F is continuous or not. So this is the way to modern topology. See, I'm yet to come to topology so far because my aim is just to motivate you what finally why topology, what it is. So first advantage is that we can do metric dependent. And now let me give some examples for you. I mean, I want to go a little further. There is still 12 minutes left out, so I will use some more time. This is a standard example in all your, what is that? High colleges you must have done. So this is the first one is I call D1. See, in R2 I'm giving two metrics. One is D1 U comma V X comma Y. The distance between UV and XY is modulus of X minus Y plus modulus of U minus V minus Y. Modulus of U minus X plus. So it is, the distance between X coordinate, modulus of the distance between X coordinate plus distance between, the Y coordinates. That's exactly the sum of them. This, what you do if you are given 2 points, you first draw vertically and then horizontally going from one point to the other. So you draw the vertical line and horizontal line, you get a what is that, rectangle. So go along the sides, that's the sum. Okay, that's the first one. Second one is a very standard example, the Euclidean distance. So both these metrics, well, I don't get into it because I assume that you must have done in your metric space theory. So to do analysis on these two metrics, I'm just trying to make some comparison. Let us first understand what are the open balls. So let's look at this. This I want you to understand that the open ball in the first metric D1 will look something like a diamond like this. The center AB, the radius R. So if you can check that distance, the boundary, if you look at the distance, that's exactly going to be, drop down and they'll go along this. That's exactly the radius. The R for all of them. Okay, they are, what is that? The square, like that is tilted there. So the open ball is the interior of this, not the including the boundary. Some of these things, I suppose, either you must have seen, if not, you can look at it. The second one you are already familiar. Open ball. Here the radius is given some S, doesn't matter, whatever it is, some positive real number. Now, what is the beauty of this whole thing? The beauty of the whole thing is, if you give me an open ball in the, so this is the open ball in D1, this is the open ball in D2. If you take an open ball in D2, it will always contain an open ball in D1. I mean, if you know the radius of the circular one, actually in this case you can take the same radius, it will be still inside. It will just touch, not anything smaller than that. So every D1 open ball contains a D2 open ball around C. And the beauty is the other way also. If you give me any D2 open ball, D1 open ball, it will also contain a D2 open ball. So this is a, the two metrics are different, but there is a beautiful, understanding of the relation between them. So every D1 open ball contains a D2 open ball. Every D2 open ball contains a D1 open ball. So what does that infer? So let us It's very general kind of a thing. So if D1 and D2 are two metrics on a space, and if every D1 open ball contains a D2 open ball, and every D2 open ball contains a vice versa, means every D2 open ball contains a D1 open ball. Then what can we say? Let us look at this. So this N is neighborhoods in D1. So U contains a D1 open ball in X. Both are in. C is fixed. I have not written that. There is a C fixed, some point C. Now, if you take any, similarly N2. N2 is all subsets. It's a D2 neighborhood. The first one is N1 is D1 neighborhood. Neighborhoods in D1 metric. Second is, let us take an element of N1. Then it will contain a D1 open ball. But every D1 open ball contains a D2 open ball. Therefore, U will contain a D2 open ball. So U belongs to N2. I hope I'm not very fast. Similarly, if you take an element in N2, subset U contained in X, U contains a D2 open ball around C. But every D2 open ball contains a D1 open ball. So it will contain a D1 open ball around C. And therefore it belongs to N1. So that means N1 equal to N2. If you have understood what I said, analysis completely depends on neighborhood system, be it determining limits or determining limit point preserving maps. But here we see that for different metrics, D1 and D2 are two different metrics. I mean, I gave some example also earlier. There are more examples I can give. The neighborhood systems are same. Therefore, the limit points are same. So many metrics you can simultaneously study. The limit concept is in D1 metric and D2 metric are same. So we can study so many metrics simultaneously if we come out of metric and get into neighborhood system. I hope you understood that. I will give one more example before I wind up. This is a very standard example. In R, I will give this. R, look at the metric DAB. This is also an exercise, yes. Is minimum of modulus of A minus B, comma 1. And let us give notation. N1 for which one? N1 for modulus, N2 for the neighborhood system in this new metric D. Then N1 equal to N2. So the two metrics are completely, quite different. I mean, one can give plenty of such examples, but they all give the same limit point concept. So what I want to stress is that it is not the metric that determines the limit point concept. Metric motivates us to define, this closeness between points and, subsets to decide. But ultimately, limit point concept is much beyond that, because so many metrics give same kind of, limit point concept. So therefore, it is not completely, determined, on the basis of, it is determined by metric, but we can do without that. We can, many metrics would give same concept. So instead of studying these metrics separately, we can study all of them together, provided we just come out of the metric and ask the question, what is the neighborhood system associated in each of them? Okay, so this is what I wanted to say. Now we will look at how this will help us to define, go further. Again, in this direction. Okay, I think I stop here. Yes. If anybody wants to ask some question or make some comment, please.
Hello, sir. Am I audible?
Yeah, audible.
Yes, sir.
Arjuna?
Yes, sir. Sir, the mention
Yeah,
about inverse image was helpful, sir. Actually, it was an ambiguity, right? Like it is considered as an inverse function. So that mention really helped, sir.
No. Okay, good. Okay. It is just a notation.
Yes.
And just one small addition I tell you, if actually f is bijective and inverse exists, then it is the image of the inverse function.
Yes, sir.
But generally it is just a notation for a set. Very convenient because it communicates what we are talking, but at the same time confusing, because people might think that I'm talking about inverse function. No. Yeah.
Yes, sir. Thank you, sir.
Welcome. Yeah, if there are no other doubts, probably it's time. Yeah. But I want more people to react. I mean, I'm not very happy with this. I keep on talking, and I don't know. I'm sure it would be boring for others. Even if it is small doubt, I mean, if it is being posted, then it would make me happier. I don't know. I can't force people, but yeah.
I don't know why
Yes.
our students are here now. First sem and basic topology they are studying in
Yeah,
first
students
semester.
should ask questions. No, that's what they should learn. Yeah. So they may be studying topology, I know.
Yes.
That's why I don't want to give definition, and that's not the way I wanted to say. I wanted to give an idea how you arrive at the definition of topology. Why should you look at it, etc. So these are the questions. But there are students from other places also, right? I mean, other colleges, etc.
Yes, sir. Students from outside Kerala also.
Okay.
Sir, am I audible?
Sophie.
Yes, you are audible. Who is speaking?
Sir, I'm Dami. Actually, my name is Dami.
Oh, I see. Okay, but what is written here? Okay, tell me.
Okay, sir, can you please show me that exercise question again? That was left as an exercise, I think so. Let F be continuous at C.
Let me see.
Okay.
Yeah, let me just go to the presentation.
Yeah, sure, sir. Take your time.
Just a minute. Exercises. So here is this exercise.
No, sir, before this. You were given 2 questions.
Yeah, I remember, but anyway, this is also This one. Here are two
Yes.
exercises.
Yes, sir. Yes, sir.
If f is continuous, then f preserves limit points. And if
Sir,
f preserves limit points, then f is continuous. The two are equivalent. I mean, you can write down this.
sir, is it a true statement, or we have to show, or we have to find a counter example?
No, both are true. If f is continuous, then f preserves limit point. In other words, I mean, more precisely, I have written, this is a true statement. The assumption is f is continuous at C. Then, conclusion is that whenever C is a limit point of f, C is a limit point of f. So, it preserves limit. This is true.
Sir, is it necessarily true?
And the converse is also true. Assume the second part, prove the part.
Sir, I have
The
a
two
doubt.
statements are equivalent.
Sir, I have a doubt if f
Yeah.
is given as continuous function, and for any subset of a with C
Yeah.
as a limit point, f of C is necessarily true that f of C is a limit point of f of a. Is
Yes,
that necessarily
necessarily
true?
Yes. That's
Sir,
what it means. No? For any
may I-
subset A with C as a limit point, FC is a limit point of F. Yeah, tell me.
Sir, if I take a function f from R to R,
Yeah.
am I audible, sir?
Let me write down. Let
May I
me write down.
continue?
Yeah. Yes, continue.
Okay.
F from R to R. What is the function?
Yeah. F of x is equal to 2. A constant
Okay.
function for all
R
x
to
element of R. If I take a function
Yes,
like this,
F of X equal
and
to.
let capital A.
Yeah, I understand your question. Yeah, tell me. Yeah, tell me.
And if I take capital A as closed interval 0, 1,
You didn't complete.
sorry,
Yeah, tell.
if I take capital A as closed interval 0, 1,
Yes.
and say A dash is equal to closed interval 0, 1, then f of A is equal to f of closed
What is A
interval
dash?
0, 1 is
A-
equal to.
What is your A? Why did you say A dashed? You're taking A, no?
Sorry, A. A is closed interval 0, 1.
What is A? Okay.
A subset.
Yeah.
Sir, am I audible?
Hello?
Hello.
Hello? Now audible. Tell me. You are taking closed interval 0,
Sir,
1
if I take,
as A, and then your function is the constant function.
yes, sir. Then f of A is equal to f of closed interval 0, 1 will be set 2, right?
Just singleton 2. Set containing only singleton 2.
Sir, but
one
singleton 2
element.
has no limit point if x. Yes, sir. If singleton 2 has no limit
Again,
point if
I mean,
x
this is
not
something-
equal to.
No. See, here is a confusion. First and foremost, what do you mean by limit point? 2 is a limit point of singleton 2.
Sir, singleton 2 has no limit point, right? If x not equal to 2.
No, that's not true. That's not true. See, this is why I kept on. This is the second. Twice I said this. This is the third time I'm telling. I don't know whether you that. What is meant by a limit point? Every neighborhood should intersect the set. Your set is singleton 2.
Right.
And the I say 2 is the limit point of singleton 2. Neighborhood of 2. It will intersect the set singleton 2. Because 2 will always be there, no, in the intersection. See, my
Sir, your
definition
voice is
of
breaking.
limit point is. Hello? Can you hear me?
Yes, sir. Now I can
Okay.
hear.
The
Sir.
definition of limit point, again check. C is a limit point of A if every neighborhood of C or every interval around C intersect A. That's all. I didn't say interval other than it should intersect at a point other than C. I understood when you said the constant function, this is what you are going to ask.
Okay.
That's why I kept on telling I'm not using the conventional definition of limit point. Because I insist this because it will not be, it is not going to be, it's only if I use this definition, it will take limit point to limit point. And I would say that limit point to limit point is a very important concept. But only thing is the language is slightly different to impress the audience. That is why interpret. Otherwise, always there will be an irritating factor of the isolated points kind of concept comes. I didn't want to get into that. So therefore, in the definition of limit point, we said every neighborhood should intersect. Only that. We don't insist on intersecting at a point other than the point itself. Is that clear?
Okay, sir. Yes, sir. Due to some network issue, I was not able to complete that. That's why, sorry, sir.
Okay.
Thank you, sir.
Okay, that's fine. Yeah. Anyway, good you ask, because it's a third. I mean, the more I want it like this so that I can explain the naturality of content. The lecture preserving. Otherwise, the naturality will be completely missing if you use some other definition. But at this point, that definition is the one that if you use that as the midpoint, the definition of limit point, then it automatically, gives you limit point preserving maps as continuous maps. Otherwise, it's going to be something else. I didn't want to get into that. Unfortunately, there is no.
Okay, sir.
All of them use the other definition, and there is no definition. There is no word used, any other word used for the concept that I'm giving. Okay. Yeah, I think we should wind up, right?
Okay, sir. Thank you, sir. And I also thank all the participants. And tomorrow we can meet at the same time, at 7 o'clock. We can meet.